Hello, in this video I will be solving problem 2.34, part A, from David J. Griffith's Introduction to Electrodynamics, 4th edition. Now, problem 2.34a wants us to use equation 2.43 and the potential that we found in problem 2.21. Now, I will assume that you've already solved problem 2.21, but I will write down the potentials that we'll be using. So in problem 2.21, you found that V of R is equal to negative from infinity to r, multiplied by 1 over 4 pi epsilon naught q over r squared dr is equal to 1 over 4 pi epsilon naught multiplied by q over r. And this is for outside the sphere. And for inside, we found v of r is equal to negative infinity to r 1 over 4 pi epsilon naught q over r squared dr minus the integral of r, large r to small r, of 1 over 4 pi epsilon naught times q over large R cubed r hat. And these are all r hats. Or not r hats, r vectors, my apologies. And this reduces down to, for inside the sphere, 1 over 4 pi epsilon naught multiplied by q over 2 large r times, in parentheses, 3 minus small r squared over large R squared. And this is for inside. So these are the two potentials from problem 2.21 that we are considering, and that problem 2.34 part A tells us to use. Now, the goal of problem 2.34 part A is to find the energy stored in a uniformly charged solid sphere of radius r and charge q. Now, what uniformly charged means is that there's a continuous charge distribution throughout the system, and we want the energy stored within. And to solve for this, we will begin at equation 2.42. 2.42 states that W, work, is equal to half the summation from I is equal to 1 to n of Q to the I multiplied by V R to the I. Now, this equation, as Griffith states, is, quote, is how much work it takes to assemble a configuration of point charges. It's also the amount of work you'd get back if you dismantled the system. In the meantime, it represents energy stored in the configuration. Now, this last sentence that he spoke, energy stored in the configuration, is the key to solving our problem. In our problem, we are considering a uniformly charged solid sphere of radius r and charge q. This means that the charge is the same throughout the whole sphere. We know the dimensions of our sphere, and therefore, instead of the summation formula, we can use equation 2.43. And as for volume charge density, rho, 2.42 becomes work is equal to 1/2 the integral of rho v d tau. Now, as part A states, we will use the potential found in problem 2.21 to solve for the stored energy. Now, relevant to our problem, we only need the potential within the sphere. And the potential within the sphere is this potential. So we only need this one, we do not need the outside potential. So we will take our problem here and turn it into, by plugging in our potential, we will get W is equal to 1/2 from 0 to r rho multiplied by 1 over 4 pi epsilon naught q over 2r 3 minus small r squared over large R squared multiplied by t d tau, in which we know d tau is equal to r squared sine theta, my apologies, sine theta dr d theta d phi. And this is because we are in spherical coordinates. So our new domain values are the w is equal to 1/2 the integral of r is equal to 0 to large r, and the integral of theta is equal to 0 to pi, and the integral of phi is equal to 0 to 2 pi. And this all is the integral of rho 1 over 4 pi epsilon naught q over 2r, and parentheses 3 minus small r squared over large R squared, multiplied by r squared sine theta dr d theta d phi. Now before we move on, something important that we can do is we can pull out the constants from within the integral. And we can do this because these values do not change in response to the integrals. So we will instead have, it is equal to 1/2 rho 1 over 4 pi epsilon naught q over 2r, multiplied by r is equal to 0, large R, theta is equal to 0 to pi, and phi is equal to 0 to 2 pi. Multiplied by, within, we still have 3 minus r squared over large R squared, r squared on the outside. Oh, no, we still have sine theta. So we have sine theta still in there, dr d theta d phi. Now, if we separate and solve, we can find that, and this is going to be a long equation, w is equal to 1/2 rho 1 over 4 pi epsilon naught q over 2r. From r is equal to 0 to large R, we will have 3 minus small r squared over large R squared times r squared dr, and the integral theta is equal to 0 to pi of sine theta d theta, and the integral of phi is equal to 0 to 2 pi of d phi, which if we solve, we will get, if we solve the integrals, or take the integrals, we will get rho q over, I believe, 16 pi epsilon naught large R, and this is from multiplying all of these together. And within our first integral, actually we won't solve for that quite yet, so we will leave r is equal to 0, r 3 minus small r squared for large R squared dr. But for our singular integral, we will get the integral of sine theta is equal to negative cosine theta, and that is from pi to 0. And then of course we just have phi, which is going from 2 pi to 0. And I'll just keep writing this out. Rho q over 16 pi epsilon naught large R, the integral of r is equal to 0, large R, 3 minus r squared over r squared dr, and negative cosine theta of pi becomes negative 1, and we subtract the negative cosine theta where theta is equal to 0, which is negative just positive 1. And then phi from 2 pi minus phi 1 is equal to 0 minus 0. And these, of course, just equal 2. That was a bad 2. And this just equals 2 pi. That's quite a bad, but you understand the premise. And so we will end up with, without taking that first integral still, rho times q over 16 pi epsilon naught large R times r is equal to 0, large R, 3 minus small r squared over large R squared, multiplied by small r squared dr. And on the outside there, or instead of dr immediately, we will have 4 pi. From 2 times 2 pi is 4 pi. So we'll have 4 pi r squared dr now. Now, if we pull out the 4 pi, as it's a constant, then we will have, if we pull out the 4 pi, then we'll have 4 pi rho q over 16 pi epsilon naught r, which will cancel out with the bottom, leaving a 4 behind here. And if we take the integral now, we will have 3 over 3r cubed minus 1 over 5. Oh, my apologies. Before we do this, let me show you us multiplying the r squared into the parentheses. So we will have the integral of r is equal to 0 to large R of 3r squared minus r to the 4th over large R squared dr. And when we take the integral of this, we will get rho q multiplied by 4 epsilon naught large R multiplied by, and the integral of 3r squared is 3 divided by 3r cubed, and the integral of r to the 4th over large R squared is 1 over 5 multiplied by small r to the 5th over r squared. And all of this is still from large R to 0. So we will end up with, and I'll write this in red, we'll end up with large R cubed minus 1/5 large R to the 5th over R squared. And for when R is equal to 0, we will have just 0 cubed minus 1/5 0 to the 5th over R squared. And this just reduces down to 0, so it subtracts 0. So we are just left with this in our integral, from our integral. So we will end up with rho q over 4 epsilon naught r multiplied by r cubed minus 1/5, and r to the 5th and r to the 2nd cancel out, so that we just have r to the 3rd left. So we have 1/5 r cubed. And now that our r's are the same value, we can actually subtract 1/5 r cubed from the large R cubed. So we end up with rho q over 4 epsilon naught large R multiplied by just 4/5 r cubed, as this is just that value. That's a horrible area. Now, multiplying this all together, we end up with work is equal to rho q r squared over 5 epsilon naught. And that's thanks to 4 rho q r squared over 20 epsilon naught. And the r on the bottom disappears from r here just to 2. And we reduce the ratio from the 20 down to 5. And that's how we get this value of W. Now, next we'd like to plug in the value for charge density, rho, given it's equal to Q. So, Q is equal to rho from r is equal to 0 to large R of R squared dr. Well, before I write this out for you, let me explain what we're doing. So we're plugging in the value for charge density rho, given that is equal to Q. So Q is equal to the integral of rho d tau, because it's spread throughout the system of the sphere. And thanks to the fact that it's continuous at the sphere, that we need to integrate it over the sphere's volume. So d tau is of course equal to r squared sine theta dr d theta d phi, which brings along its r is equal to 0 to all large R, theta is equal to 0 to pi, and phi is equal to 0 to 2 pi. And this multiplies, or is the integral of r squared sine theta d dr d theta d phi, which if you take each of them, I will show you the integrals. Q is equal to rho multiplied by 1/3 r cubed from r to 0, negative cosine theta from pi to 0, and phi from 2 pi to 0. And this reduces down to 2 pi minus 0, which is equal to 2 pi. And this reduces down to the same from before, which is -1, -1, minus -1, which is just equal to 1 plus 1, which is equal to 2. And this reduces down to 1/3 large R cubed minus 0, which is just simply 1/3 large R squared, or cubed. So we will end up having Q is equal to rho times 1/3 R cubed to 2 pi, which when all multiplied together gives us rho is equal to 4 pi R cubed over 3. Now, therefore, charge density is by moving values around to the left side. So moving this over here to get rho by itself, we have 3Q just divided by 4 pi R cubed. So now that we have our charge density, we can plug it back into our value or our formula from before, which is just here. So plugging rho back into that, we will end up with W is equal to rho QR squared over, one moment, just by moving down rho. We end up with 3Q over 4 pi R cubed multiplied by R QR squared 5 epsilon naught to get a total of 3Q squared over 20 pi epsilon naught large R. So by pulling out 1 over 4 pi epsilon naught, which is just a common value, pulling out 1 over 4 pi epsilon naught from this formula, then we end up with our final value for work, or energy stored in the system, of 1 over 4 pi epsilon naught times 3/5 Q squared over large R. And with this, we have found how much energy is stored in a uniformly charged solid sphere of radius R, large R, and charge Q, using the potential found in problem 2.21. Thank you.